Okay, we were discussing about OFDM transmitter, and we were about to discuss the last block in the transmission, that is cyclic prefix. Cyclic prefix. First of all, we'll see why do we need a cyclic prefix. What are the practical difficulties when you try to transmit OFDM signal as such? Without adding a cyclic prefix, if you transmit the OFDM signal, what is the problem that you're going to face? We'll see about that first, and then from there we'll try to develop the idea of a cyclic prefix. All right. So you have the, I'm not going to draw the whole transmitter diagram again. Let's assume that you have an OFDM transmitter. Okay, OFDM, let this be the IFFT block. The IFFT block, and after IFFT block you are transmitting the signal to the transmit antenna, and I have not considered cyclic prefix block here. So without the cyclic prefix block, we'll see what is the issue that is going to happen, and then we will try to develop on the idea why should we add a cyclic prefix, and what should be the length of cyclic prefix and things like that. So this wireless channel, it is usually a multipath wireless channel. It is a multipath channel, and with channel coefficients, the channel coefficients, or you can say the channel impulse response. We have discussed that before. Channel impulse response is given by h of 0, h of 1, etc., etc. It goes up to h of mu. Okay, this is the channel impulse response. And how many points or how many coefficients do you have here? You have mu plus 1, mu plus 1 length channel. You have a mu plus 1 length channel. The channel is having impulse responses which has mu plus 1 number of points. Okay, now you are transmitting the signal. Let's say you are transmitting the signal. Okay, you are transmitting the signal x of 0, x of 1, etc., etc. You have n number of points in your OFDM signal. So this is your OFDM block. You can say OFDM block. X of 0, x of 1 up to x of n minus 1. You have n number of points, so you have x of 0, x of 1 up to x of n minus 1. So when you transmit this signal, it undergoes a linear convolution with the channel impulse response. Okay, we have seen that also. Okay. So the impulse response. Here you have h of 0, h of 1, etc., etc. goes up to h of mu. It is a mu plus 1 length. It is a mu plus 1 length channel. When the linear convolution happens here, at this point you would get x of 0 into h of 0, which is y of 0, and y of 1. For y of 1, this block would have moved to the right. This block would have moved to the right. That is, let me try to copy the block. This block initially it is here. For y of 1, that is the next time instant, it moves here. So you would expect, let me just draw that here. Yeah. For the next time instant, y of 0 is h of 0 into x of 0. Y of 0, y of 1, here you get y of 1. So this corresponds to y of 0, which is x of 0 into h of 0, and here this is y of 1, which is h of 0 into x of 1 plus h of 1 into x of 0. And you would expect a transmission like this, that is a linear convolution of this x of n convolution with h of n, the impulse response. But this doesn't happen. The reason is that OFDM transmission is we transmit block by block. So OFDM transmission is a blockwise continuous transmission. It is a blockwise continuous transmission. Okay, because it is a blockwise continuous transmission, this doesn't happen, which means that before this block, there could be another block, the previous block, right? So that is a possibility. Let me just copy this, and let me demonstrate that to you. Okay. There could be another block before this transmission, and it could look like this. I'll draw another block. This is the previous block. Here you have similar to this, you have x of n minus 1, x of 1, x of 0, and to differentiate between these blocks, let me just name this as, this is my my first block, So I'm giving the subscript x1 of 0, x1 of 1 up to x1 of n minus 1, and this is my previous block. So let me name it as 0th block, and this is x naught of n minus 1, x naught of 1, and x naught of 0. Let me name it like this. And again, the impulse response comes into picture, and we'll see what happens. So this is how OFDM transmission works. So you have 0th block getting transmitted, and then first block getting transmitted, and then second block getting transmitted, and like that blocks are continuously getting transmitted. And because of that, this type of a response is not possible. Okay, so this is not possible because OFDM transmission is blockwise continuous in nature. So let me show you that. Okay. Now I'm trying to sample this first block. I'm starting to sample the first block. And what is the signal that I get here? What is the signal that I get here? The signal that I get here is y of 0. So I expect it to be y of 0. But what happens is I have h of 0 into x1 of 0, h of 0 into x1 of 0 plus h of 1 into, it corresponds to the previous block. So let me denote that by red color. H of 1 into x naught of n minus 1 plus etc., etc. It goes up to h of mu into, so which will be the symbol here corresponding to uh, x naught, this block x naught. So x naught will have it will have okay, mu number of symbols, which means this convolution happens up to h of n minus mu. Convolution happens at up to x naught of n minus mu. So here you have this symbol, which is our symbol of interest, which is a symbol which is a symbol that belongs to the current block. Okay, it is a symbol that belongs to the symbol of the current block. And while I am sampling this particular symbol, mu number of symbols of previous block, all these are mu number of symbols of previous block, also gets added with the current block. Mu symbols of previous block. So the current block is block 1 and the previous block is block 0. Mu symbols of previous block also gets added with, which means this is inter-symbol interference. This is the phenomenon of inter-symbol interference, ISI, or inter-symbol interference. So when I am trying to sample signal the sample of the block number 1, the first block, mu number of symbols of previous block also gets linearly added. There is a linear addition of mu, but I don't need those symbols. Okay, which means there is an inter-symbol interference from previous block. Okay, so this inter-symbol interference happens, and this happens at y of 0. And what happens at y of 1? What happens during y of 1? During y of 1, this impulse response, the operation of convolution happens. It moves here, and you have, in a similar way, you will have here y of 1, which is h of 0 into x1 of 1 plus h of 1 into x1 of 0 plus etc etc. It goes up to h of mu into here it went up to x of n minus mu. Okay, and so now this would end at the symbol just after that, the x of n minus mu plus 1. Okay, so here there is again there is ISI. So these are symbols which are belonging to block 1, right? And you have the rest of the symbols, the rest of the addition terms you have as ISI. Okay, mu minus 1 symbols, from the previous block gets added, and this happens in the symbol. And so x1 of 0 has ISI of mu number of previous symbols, x1 of 1 has ISI of mu minus 1 number of previous symbols, etc etc. This can go up to which case? This impulse response after each of the time instants, it can reach here at this point where you don't have inter-symbol interference from the previous block. You have all the symbols from here, from this block. Okay, so I'm asking you, how many symbols got affected by the inter-symbol interference? How many symbols got affected by inter-symbol interference? The answer is, when the impulse response was here, x1 of 0 got affected. When it is here, the next time instant, x1 of here x1 of 0 got affected, here x1 of 1 got affected, and this goes up to this point. At this point where the symbol here will get affected, and it reaches at this point where there is no interference from the previous block. So how many symbols would have got affected here? Mu number of symbols, starting from h of 0 up to h of mu minus 1. There are mu number of symbols getting affected by inter-symbol interference. Okay, I hope that idea is clear for you. Mu number of symbols are getting affected by inter-symbol interference. So after each time instant, this impulse response moves towards the right, and till this point, at this point, you have just h of mu into x naught of n minus 1, and here you will have mu number of symbols getting affected by inter-symbol interference. Okay, from this point, the very next point, you will not have any inter-symbol interference from the previous block. So that is one of the idea that you can get from here, that is mu number of symbols are getting affected by inter-symbol interference, mu number of symbols, let me be specific, of current block, of current block, are getting affected by ISI, inter-symbol interference, from the previous block, So how can I avoid it? How can I overcome this disadvantage? We'll think of ideas. One of the very straightforward idea that you can have is you leave mu number of symbols here. Okay, you just leave mu number of symbols. You transmit the first block, the zeroth block, and after a gap of mu time instances, that is the time required for the impulse response of the previous symbol to die out. Okay, the time required for the impulse response of previous symbol to die out, you don't do any transmission, and then you transmit the first block. That is one of the straightforward ideas that comes to the mind. Let me just draw that. You have x of 0, x of 1, etc., goes up to x of n minus 1, and the idea is for mu number of, let me draw with another color. Okay, then you have the previous block. That is x of 0, x of 1, etc., x of n minus 1. Here you have mu sample points. This is the block number 1, so I denote it by 1. This is block number 0, I denote it by subscript 0, which is the previous block. So how will I remove inter-symbol interference? Let me just copy this. Yeah. If I have this impulse response as it moves from the previous block, 0th block, and mu number of sample points, it is not getting affected by the previous symbol because I have not done any transmission. So it is just 0. I'm not explicitly writing 0. Just remember that there is no transmission during this time. We haven't reached cyclic prefix yet. We are thinking of ideas. One of the straightforward ideas is you don't have any transmission for mu number of sample points, which means that simply you are allowing the impulse response of this 0th block to die out. After mu number of sample points, it slowly dies out, and then you can start with this the current OFDM block. the impulse response, the tail of the impulse response of the previous block has slowly died out, and you can start here. But again, a problem arises that at the receiver, let us see how the signal structure is. Let me go to the first diagram. So you have an IFFT performed, that is, you have converted the frequency domain x of f into time domain x of n, and then you are transmitting this through the channel, and the channel gives you a linear convolution x of n convolution h of n. At the receiver, what happens? This is a receiver, OFDM receiver. You have x of n convolution h of n here at the receiver. But how will you decouple these signals? That is a question. Because you want to separate out x of 0, x of 1, etc., up to x of n minus 1. But in order for you to separate this is a convolution operation. That is, a convolution operation is a complex operation. So when you have a convolution product, so you will have y of 0 is x of 0, h of 0, y of 1, x of h of 0, x of 1 plus etc., etc. You this convolution is a product and sum. First you multiply and then add this, and it goes up to y of n minus 1. And how do you decouple all these signals? How do you separate out the signals? So that is a question, that is a challenge at the receiver. So here y of 0 you can have x of 0 and h of 0, y of 1 you can have h and plus h of 1 into x of 0, y of 2, and as a convolution goes on, this addition terms increases. It increases in number, and but what I want is, I want to extract x of 0, I want to extract x of 1, I want to extract x of 2. But when these symbols are undergoing a convolution operation at the receiver, there is no way I can. There is actually a challenge for me. I need to decouple, or I need to separately detect this signal. I need to separate out these signals x of 0, x of 1 up to x of n minus 1. I need to separate out these signals. For that, the idea is, if I had a circular convolution, okay, if I had a circular convolution, then a DFT at the receiver, circular convolution of x of n with h of n, and a DFT at the receiver would give me x of f into h of f. Okay, so this would be my received signal, which is y of f. Okay, from here I could separate y of 0 is x of 0 into h of 0, y of 1 is x of 1 into h of 1. Okay, remember this is a frequency domain. I'm taking a DFT here, so I'm talking about frequency domain now, and I can very easily separate out signals. X of 0 is y of 0 by h of 0. Here x of 1, which is y of 1 divided by h of 1. In order to enable this, this should be a circular convolution. But in reality, what happens is a linear convolution. Because in every case, every wireless communication channel, the channel does a linear convolution. That is true for all systems. The input with the impulse response, always it is a convolution operation. It is a linear convolution operation. So I'm finding ways to convert linear convolution to a circular convolution. So how will I do that? My intention is to convert the linear convolution, that is x of n convolution h of n to a circular convolution. That is x of n circular convolution with h of n. The channel is not circular in nature, but the channel should feel like the receiver should feel like the channel is circular in nature, or the receiver should feel like a circular convolution is happening. So how will I make this linear convolution to circular convolution? So my idea is to place mu number of points from here. Okay, my idea is to place mu samples. Anyway, I have mu slots here. I will place mu sample values. Okay, I place mu samples from the tail, from the last mu samples. I will place the last mu samples. So which are the last mu samples? I have x1 of n minus 1 here, x1 of n minus 1 here, and I will place from mu number of, what will be the sample, what will be the sample here would be x of n minus mu. So in total, how many samples do I have? This minus this plus 1, right? So n minus mu minus n minus 1 minus n minus mu plus 1. So n and n gets cancelled. Minus 1 and minus 1 cancel. So I have mu number of sample points. So I have, I will place these last mu samples here, which means I have x of n minus mu, x of n minus mu, etc., etc., goes up to x of x1. Remember, it is x1. x1 of n minus 1. So this symbol would be x1 of n minus 2. What I've done is I've placed these last mu samples. Here. I had mu sample points here. I've placed last mu samples here. And I will see how this channel converts this linear convolution into a circular convolution. So how does the channel do that? So when I have here, let me draw a more general diagram. So now I've got the idea. This is the cyclic prefix. These last mu samples, placing that before the symbol. Okay, placing last mu samples of current OFDM block to the front of the block. So I am adding it as a prefix. Okay, I have added this as a prefix, and it is cyclic in nature. We'll see that it is cyclic in nature. Okay, it makes the linear convolution into cyclic convolution. It makes it a cyclic nature. And yeah, let me draw another diagram. Will make it more clear for you. So this is x of 0. I'm dropping subscript now. For easiness, I'm dropping the subscript now. It is just x of 0, x of 1. It goes up to from x of n minus mu to x1 of n minus mu, I'm placing it as a prefix. So let me mark that also. Because that's a significant point. That is where the cyclic prefix starts. X of n minus mu goes up to x of n minus 1. So this is your current OFDM block, and you are placing these symbols to the front. Placing these symbols. Copy well. Okay, I'm placing those symbols to the beginning, and this is nothing but this is the cyclic prefix, CP, cyclic prefix. Prefixing the last mu number of symbols to the front of the block. So that is a cyclic prefix. And for clarity, let me also draw the previous symbol. Okay, it was x naught of n minus 1, etc., etc. X naught of 1, naught of 0. Okay, so now we'll see how this cyclic prefix will convert the linear to circular convolution. So let me just copy this block. Yeah. So the convolution happens, the linear convolution happens. It happens to this block, the previous block, and then this convolution moves here. Okay, and you know there are mu number of samples here. Okay, there are mu symbols for cyclic prefix. There are mu symbols for cyclic prefix, and as such, so when I move this impulse response block to each point, you can compute the corresponding convolution. So here there is intersymbol interference, n minus mu getting interfered with the previous symbol. Here again there is intersymbol interference, this symbol, and intersymbol interference will happen till this point where here there are mu plus 1 symbols, and here there are mu symbols. It happens till this point where here you have mu number of symbols. I'm not considering h of mu, here mu number of symbols, and here you have mu number of symbols which belongs to a cyclic prefix. You will have ISI up to there, and let us see something interesting happening now. And as such, it moves here, it moves at this point, yeah, this point, where h of 0 gets multiplied by x of 0. Okay, let me just write it as y of 0, y of 0 equal to x of 0 into h of 0 plus Maybe I will write that towards the right side. Yeah, y of 0 is equal to h of 0, x of 0 plus h of 1, x of n minus 1 plus it goes up to h of mu. So it is a mu plus 1 length channel, so it goes up to h of mu correspondingly. You will have here x of, here you have mu number of symbols. H of 0 is getting multiplied with x of 0, and from h of 1 to h of mu we have mu number of symbols, so you have n minus mu, the h of mu getting multiplied with x of n minus mu, n minus mu. And then at the next time instant, your impulse response, it gets shifted towards right, and here at this point you have y of 1, which is h of 0 getting multiplied with x of 1 plus h of 1 getting multiplied with x of 0 plus etc etc plus h of mu into, which will be the symbol here, it will be the symbol just after x of n minus mu, so x of n minus mu plus 1. And this sampling, it goes like that. This impulse response, which is here, it moves like that, n number of points. It started from here and it moves n number of points, which means it reaches here where h of 0 getting multiplied with x of n minus 1. Okay, and I have here the result of that convolution. Now this is taking a little long. Please stay with me. Let me complete this. You will not get the flow if I stop in between and start the class next day. So let me just complete this portion. So y of n minus 1 is equal to h of 0 into x of n minus 1, h of 0 into x of n minus 1 plus h of 1 into x of n minus 2 plus it goes up to h of mu into, so from here it goes up to mu plus 1 symbols, so it is x of n minus mu minus 1. Okay, is that right? So I have n minus mu minus 1, n minus mu minus 1, and I have here x of n minus mu, n minus mu plus 1. So I want to count how much is the number of symbols that I'm getting. I want to know if my subscripts are getting wrong. So n and n gets cancelled, mu and mu gets cancelled, and minus 1. Oh, sorry. N minus mu minus 1 minus n minus 1. Right. So n and n gets cancelled, minus 1 minus 1 gets cancelled. I have, yeah, new number of samples. Correct. And what do you see here? What do you see here? If I represent this as a matrix, it would look like y of 0, y of 1, etc., etc., up to y of n minus 1. This is equal to, I can write, so this matrix is getting multiplied with the this channel coefficients h0, h1 up to hn, h of nu. So I can either write like I can write it like the channel matrix h of 0, h of 1, etc. into the symbols, or I can write symbols into whichever way I write, it will look cyclic. So let me try to write in a different way, or let me just write in the way it is more comfortable. That is x of 0, x of n minus 1. I'm just trying to write this equation, etc., etc., up to x of n minus mu. Again, you have here x of 1, x of 0, etc., etc., up to x of n minus mu plus 1, etc., etc. It goes. Y of n minus 1 is x of n minus 1, x of n minus 2, etc., etc. It goes up to x of n minus mu minus 1. And I have this matrix getting multiplied by h of 0, h of 1, etc. up to h of mu. I have taken these equations and I have made it into a matrix form, a matrix representation, and you can clearly see there is a circular convolution happening, because see the row x of 0 up to x of n minus 1, and in the next step the term here has come up, x of 1 has come here, this whole term has shifted to the right, and you have here this term in the first row has shifted to the right, etc., etc. Shifting happens till this point, and from this point again, if another shift happens, then this first row will come up. So this is one way of seeing that it is in fact a circular convolution happening. Circular convolution is happening here. Or another way you like to see is to write the coefficients in a slightly different way. So let me try to write in that way also. This would look like y of n minus 1, y of uh, y of 0, y of 1, etc., etc., y of n minus 1, this matrix, I'm going to multiply this with the symbols. X of 0, x of 1, etc. up to x of n minus 1. We'll see y of 0. Y of 0 is x of 0 getting multiplied by h of 0. You have h of 0. X of 1. X of 1 is not in this picture. So you have x of n minus 1 getting multiplied by h of 1. So you have here h of 1. And if you see h of 2 will get multiplied by x of n minus 2. Right? So you have here h of 2 dot dot dot. And y of 1. In y of 1, if I see x of 0 getting multiplied by h of 1, and x of 1 getting multiplied by h of 0, etc., etc. It can go up to x of n minus 1, x of n minus mu plus 1. This whole thing is going to shift to the right. So it's going to be h of 2. Right? Here it's going to be, if I write h of 2 into x of n minus 1. So h of 2 is getting multiplied, x of n minus 1 is getting multiplied by h of 2. So I can write h of 2 here, etc., etc. It goes up to y of n minus 1, where x of n minus 1 is getting multiplied by h of 0. So you have here h of 0. X of n minus 2 getting multiplied by h of 1. So you have here h of 1, etc., etc. X of 0 will get then multiplied by okay, you cannot surely say for what it is, but you can clearly see that there is a circular convolution happening. Here you have this row and it is getting shifted to the right, and it goes like that up to here, and you do one more row, one more circular shift, and you get this, you get back this row. So it is in fact y of n is equal to h of n convolution x of n, or you can write it as x of n convolution h of n. So there is a circular shift that is happening. And why did this circular shift happen? It happened because you have added the cyclic prefix, and because of the addition of cyclic prefix, when you sample even the first symbol, it feels like the symbol is periodic in nature because the previous samples are coming up. The previous samples came up because of the addition of cyclic prefix. Okay, so that is what happening here. And I want you to note 2 points. One is that when you add the cyclic prefix during the transmission, you start sampling from this point. Okay, the sampling starts here when your h of 0 is here, h of 0 into h of 0. So your sampling starts from this point, and you have mu number of symbols before that. Okay, the cyclic prefix is also part of this transmission block, so you have mu number of symbols before that, and all the mu number of symbols before, they are eliminated, they are neglected. So mu symbols that undergo ISI are neglected. They are neglected. Secondly, what should be the size of the cyclic prefix? If you have a mu plus 1 wireless communication channel, a multipath channel having mu plus 1 channel coefficients, then your length of cyclic prefix must be mu. Length of cyclic prefix must be 1 less than the total length of the channel. Okay. So with that, I'll end the class for today. We'll see you tomorrow.